Good afternoon. So in the last class, we saw a nice example with geometric random motion, right, of how the Statanovich limit appears as the right white noise limit when you have a fast process driving a system. So we took the example of Brownian, geometric Brownian motion, right, but realized it by using smooth random noise. So we created this Fourier function with many random Fourier components, and we could control how fast the function oscillated in time. We also made sure that the variance of the function would grow as the correlation time went down so that it would mimic white noise. And after doing this, we saw that if we then do simulations of this equation, right, for the equivalent of the geometric problem. So we had dx dt is equal to x times this fluctuating function, right, which was nevertheless smooth in time. So if we took a sufficiently rapidly fluctuating case, that means in that case the correlation time of this signal, if I were to measure it, I make it sufficiently small, right, then you see that actually you get some kind of highly fluctuating time series which starts looking like Brownian motion. And in fact, if you solve this x times this function, that dx dt is equal to x times the forcing function, you found that the mean grows exponentially and the variance grows exponentially and even faster. So that gives you the behavior of Statanovich, correct? Because if it was converging to the Ito case, then the mean should be 0, which was not happening, right? The mean was growing. Rather, the mean should be equivalent to the mean of the initial condition, but that didn't happen. So it seemed to go to the Statanovich case. In the last lecture, we showed it qualitatively, but if you do many more ensembles of those simulations and plot it on a semi-log, you should be able to verify the analytical predictions from Statanovich that we did in an earlier class. So this will be an assignment later on. So that brings us to this interesting thing, right, that when we have physical processes where things are happening smoothly but on some fast time scale, and we are interested in looking at that or related processes which are being driven by that on a longer time scale, then we can approximate the fast process by a noise. This was the whole motivation right at the beginning of the course. And I've said that the Statanovich is the right limit, and we saw just an example in the last class. Now there is a theorem by Wong and Zakai which establishes this, but only for 1D, right? So one-dimensional stochastic processes. Okay. It turns out interestingly that if you have multi-dimensional process, that means you have many different noises all feeding into your system, then this need not happen. Okay, there are some extra caveats. And this is important when we want to model turbulence, because turbulence is, depending on what you're trying to look at, is not just one variable, right? Ideally, let's say the velocity field is somehow affecting your problem, either your transport or by creating a fluctuating force. To model the turbulence, I have to model the entire field, right? So it's not going to be just one number. It's not one dimension. Even if you say, okay, I'm going to represent my velocity field, you can use Fourier components again, right? But each Fourier coefficient will fluctuate randomly. It's just what we saw in the last class, right? Something similar. But now it is different coefficients in the Fourier series in space. Time, everything is fluctuating. But because I have a velocity field, I can write the velocity field as a sum of different spatial Fourier modes, each of which has a fluctuating noise. So in general, we will have a multidimensional noise which is affecting your problem. In that case, the limit is not always Statanovich. And in fact, in turbulence, there is an important caveat. Okay. So, but to be able to appreciate this, I thought it would be nice if we get some more insight into how one gets this limit, right? How the Statanovich arise. So I have not shown you this yet. I just showed you an example that works out. And I gave some motivation for it in a very loose way by pointing out that Statanovich follows the regular calculus, which should hold for any normal ODE, right? And if you want to say that your white noise is the limit of some highly fluctuating forced ODE, then maybe you expect Statanovich. But as we will see, this doesn't always happen. Okay? So I thought it would be nice to look at this more carefully. But to do this, we need some mathematics. Okay? And that's what I'm going to do in this and the next class before we revisit this problem. And what's the heart of the issue really is that you have some highly fluctuating process, right, and a much slower process. Okay. Now this highly fluctuating process, if you are living in an ODE world right now, is also following its own dynamics. So one way of, this kind of question of how to replace the fluctuating process, right, in some effective way is closely related to if you have a large dynamical system in which some degrees of freedom are evolving fast and some slow. How do you simplify this to equations only for the slow processes? It's essentially the same question. It's just that we say that now the fast processes are so fast that I can treat it as noise and fluctuating in some kind of way that it has zero average and so on. But if you broaden this question, it's like saying, okay, I have many variables in my system. Some variables are the ones I'm really interested in and they are evolving slowly. And some other variables I don't know much about. You can always write some model for it, but it won't be very accurate. And in the end, I don't care because they fluctuate super quickly. And somehow I only want their mean effect. Okay, so the question is, how do I get if I have a big system with fast and slow variables, how can I get equations for only the slow variables? Okay. And somehow we will see that in our context, if the fast variables are starting to behave like white noise, then the effective equations for the slow variables will become SDs with Stratonovich or some corrected Stratonovich. This is the question. So before we can approach the more complicated stochastic problem, it would be nice to see how one does this, what is called model reduction, in a normal ODE setting. Okay, so we're not going to worry about right now for things becoming stochastic or SDs. We're just going to say I have a system of ODEs, right, or PDs, right, and there are some parts of the system which evolve quickly, some parts which are slow, and I want only the slow dynamics, okay, because that's what I'm interested in. Then how do we get an equation for the slow processes? Okay, so that's what we're going to do today, and as we go along, I'll introduce more formalism, and we will see remarkably that these ideas directly are relevant to when we try to derive the white noise limit and try to get this Stratonovich case, whether it is or not. Okay, so before talking about things more abstractly, let's look at an example, which is on this slide. Okay, so this is a nice simple 2D dynamical system. Okay, you have two equations, two variables, x and y, and you can see that this is a very simple case in which the dynamics of x are independent. Okay, so x dot evolves as minus epsilon x, that epsilon is going to be a small parameter. And then you have a second variable y dot, okay, and that evolves quickly. Quickly why? Because the leading dynamics is y dot equal to minus y. Okay, so it's a rapid evolution. And x is going to be relatively slow when epsilon is small. Okay, so this is a very simple specific example of a system where I have one slow variable x, one fast variable y. Now this is not particularly interesting because if I only wanted the slow dynamics, I can just forget about y. Right? I'll just solve for x, and x will be epsilon x. But more generally, you could imagine that x dot will be equal to some function of x and y. Okay? So while we keep this very simple example to keep things concrete, I can also write more generally. Okay, so anyway, I can do this in different ways, but let's say, let me write it in this way for now. It's not completely general, but just to make the point. Okay, so this g is some arbitrary function. The point is that overall its dynamics are slow. Okay, and y dot is minus y, right, plus, as I have written, some other function. Okay, the form in which I have written this here on the board is important because what you want is the fast dynamics should be stable. That's why I have written it as minus y. Okay. This other stuff will also have an epsilon. Okay. So what I'm saying is I have some system y where y is evolving quickly, okay, but in a stable way. That means it's not going to infinity. Right? Otherwise, you cannot model the system. So you have fast dynamics, but they are relaxing, which you can see. If the larger y is, the faster it will come down somehow. But it doesn't go to 0 because you also have this other term sitting here. So it is relaxing to something quickly. And then if you look at x, x is evolving slowly because its time derivative is small because of this epsilon. Right? But whatever that evolution, slow evolution is, it depends on x and on y. So now in this case, I cannot simply say, okay, let me forget the fast variables, right, and set y to, I'll just ignore y. I can't do that because y is sitting inside this function g. So if I want to know x evolves accurately, I need to know what is y. Okay, so I can't just throw away this equation. But what I would like to do is get some approximation for y such that I no longer have to solve the bottom equation. I can only solve the top, right? So what I would like to do is replace y in 1 in some approximation, right? Right, so what I'm saying is I want to replace y by some approximation, right, somehow. And if I can do that so that I can get rid of it, then I will get some effective equation. Okay, so let's go back. So basically the point is, can I find how y depends on x so that I no longer have to solve the y equation? Okay. So let's go back to a simple example in this context. Okay, so let's first see what I mean by slow and fast by looking at some simulations. Okay, so the curves are not so clear, but what I've done is I've taken the first quadrant, I've seeded some initial conditions, and I've just solved it. Okay. And then you will see how those trajectories evolve. Okay, so let me play that again. The dots are the actual the states of the system in phase space, and the trajectories are also drawn. Okay. Y is the vertical direction, x is horizontal. So you see very quickly that now it's going backward, just so that you can see it again. Right, so very quickly the trajectories move rapidly in the y direction somewhat. Right? Then they collapse onto some curve and then slowly evolve. Okay, they are eventually evolving towards the origin in this simple problem. Okay, because as you can see, everything will collapse. Right, x by itself will go to 0, right? And then y also will go to 0. So ultimately you will go to the origin. But the evolution has this two-step process. Okay, rapid relaxation and then a slow evolution. And that's also evidenced by the fact that all the trajectories you see are collapsing onto a curve. Okay. This curve is called the slow manifold, okay, or the center manifold. And it has to do with the fact that precisely this, that all the trajectories come quickly because of the fast dynamics being dissipative, everything relaxes, and then it sits on some curve. Okay, manifold is just a word for curve in high dimensional space, because you can generalize this beyond 2D. Right? So imagine on some high dimensional thing, all the fast variables will collapse. Right? So when I say dissipative, there is some frictional process through which things are, the high energy modes are getting damped out. Okay, and you collapse onto some row dimensional structure. In this case, this is what you can see by the eye. Right? All the trajectories collapse. And then the system evolves sitting along that structure itself. Okay. So this is called the slow invariant manifold, right, which exists in such systems when you have this separation of time scales. There is some formal mathematics called the center manifold theorem for finite dimensional systems, which I will not get into. Okay. But typically we will come to it in a second. It happens when some of the variables are slow, in the sense that when you look at the linearized dynamics, they have 0 eigenvalues. That's what will happen here. If I take the case of epsilon going to 0, trivially x dot is 0, it has a 0 eigenvalue. Right? Whereas y will have eigenvalue -1. Right? Anyway, so we'll come back to that. So when you have this kind of structure, you will be able to, one can prove for finite dimensional systems that you will have this kind of curve. Right? And it is slow because the dynamics are slow. It is invariant because once you're on the curve, you never leave. That's what you can also see in the picture. Right? If you start away from the curve, very quickly you will come to it and then you'll stay on it. So that means this curve will give me the basis of approximation. Right? Because even if my initial conditions are away from it, I will quickly collapse. So I can, if I don't worry about the very initial transient and I'm interested in long-time dynamics, the long-time dynamics will be given by what's happening on that curve. Right? And that curve here is just y is some function of x. If I can find that curve, then I can approximate by dynamics. Right? So there is a slow invariant manifold, which I'm going to call H now. So here I would put H of x. Okay, so this is the slow invariant manifold. Once I'm on it, I don't leave. Okay, so on this manifold, right, because it is invariant, it means that the dynamics keep me there. So because I'm always there, I can write y dot, right, is dou h by dou x, x dot. Right? That's why it is invariant, because once I hit the manifold, the dynamics of y are governed by this. So I can use the chain rule and write it like this. Okay, but I also know y dot independently, correct, from here. Okay, so if I substitute in 2, we can get an equation for the h of x. So I will have, in this example, and x dot is epsilon okay. So this gives me an equation for this manifold. In general, I cannot solve this equation directly. It's a fully nonlinear equation. Right? If I could, this is equivalent to solving the full system. But what I can do is I can make an approximation. So because epsilon is small, and that's when I'm saying the slow manifold will exist. Right? If epsilon is not small, none of this will happen. It's only because epsilon is small that there is a separation of time scales. So staying consistent with that, I can solve this equation. Right? So sorry, I should replace y by h everywhere. Right? So I can solve this equation for h. So I can solve for h when epsilon is small. So I do some kind of perturbation expansion, right, which I will come to later, and I can get an approximate solution for h of x. So for example, I can get h of x is h naught plus epsilon h1 plus epsilon square h2. Okay. The exact form would depend on your problem, but you can try to get some approximation for the h when epsilon is small, right, using perturbation methods or other things. Okay, but the point is now, suppose one way or the other, if I can find this h, right, then I get my reduced equation. Right, in the general case, as epsilon times g of x comma h of x. Right, where y is replaced by h. Right. Okay, so the idea is actually quite simple. The main thing is the recognition that when you have a system with widely separating time scales and the fast dynamics are stable, right, then they'll cause the system to collapse onto a low dimensional manifold. The question then is, what is the manifold? If you can find the manifold, the equation for the manifold, right, which I can generally write as the fast variables being some function of the slow variables. This is in 2D. If I generalize it, I will have y1 till yn. So, example, y1 can be some function of x1 till xm, whatever. So I can generalize this kind of thing, but all the fast variables are some function of the slow variables, right? If it is 2D, then this is a curve. If it is 3D and there's two fast variables, then I'll have some kind of surface, right, and so on. Okay. Sorry, if there's 2D and there are two fast directions, I'll again get a curve. Okay, but y1 and y2 will become functions of x. So y1 will be h1 of x, y2 will be h2 of x. If there are n dimensions and I have two slow variables, and everything will collapse on a surface and so on. Okay, so that's why it's a manifold. But fine, I need to know this thing. Right? I recognize this exists. If I can calculate it, then it's simple. I just have to go to my equations for the slow variables, and wherever the fast variables come, replace them by this manifold. I'm allowed to do that because when I hit the manifold, I never leave. It's invariant. Right? So along the manifold, the fast variables will always be given by that function. Now the question is how to find that. Right? You can say, okay, let me look at the simulation, do many simulations, I'll find they all collapse on some curve and I can extract that curve. Right? You can see it happening here, right, in the picture. Right? So imagine you do many simulations, numerically you will kind of approximate that curve if you throw out the initial transient. That would be a data-driven approach to getting the manifold. Right? That's become increasingly popular now with complicated problems, high-dimensional problems. Right? So you can use various techniques of data analysis, machine learning, and so on to try to extract that manifold from experimental data or simulation data. The older, more traditional way, which is still powerful, right, especially for not very large systems, would be to use the fact that it is invariant, right, and come to your equation for the fast variables. And then you write that the fast variable time derivative is nothing but dh by dx x dot, right, in the generalized multidimensional version. So you will get equations for the slow manifold, right, from the fact that it is invariant. Of course, you cannot solve that directly, you have to solve it approximately. So then you can use perturbation techniques. So traditional perturbation methods would follow this approach to approximate the slow manifold. But then, of course, this is not easy to do if you have a large system with complicated functions. So an alternative, which is now more popular, is to do a data-driven technique. But either way, the goal is to find the manifold. Fine. So let's go back to our example and see how it works out here. So once again, let me play this movie, right? What we want to do is find that surface to which all things are collapsing. Okay. So let's go to my simple problem. So it's nice to see this same problem arise in a slightly different guise. Okay. So I showed you the problem where time was scaled with the fast time. So if I take t to be scaled such that I'm following the process on the fast time, then the slow thing will have an epsilon in front of it, right? So you get x dot is epsilon x. So x you can see is slow because I'm looking at the problem on the fast time scale. If I flip it and say, no, let me non-dimensionalize with the slow time scale, then I'll get x dot is equal to minus x because that is my reference thing. The fast process will get an epsilon in front of its time derivative, okay, so which you can see on the board, on the slide. So you look to the slide and you see that if I switch the time scale, right, to a slow time, then the x equation is x dot equal to minus x, but the y equation, the epsilon will pop in front of the y dot. Okay? So now you can see that in terms of the slow process, if I scale that, that becomes the normal speed, right? X is evolving on normal speed, so to say, and y is evolving super fast, right? Which is like saying it very quickly stops evolving. So if I put epsilon to 0 in these equations, the time derivative of y will drop out, and you will get some direct relation for y in terms of x. This is the equivalent of the quasi-steady approximation, right? What's called a quasi-steady state. So in many, especially in engineering, you will find the problem posed like this, right? Where you have some time dynamics and some very fast processes where epsilon will multiply the time derivative, which means the time derivative has to be very large for that term to be relevant, and that is the case. But because you're interested in long time, you just say, let me drop these epsilon terms. So if I drop this epsilon y dot, I'll just get some relation for y in terms of x directly. Is that the slow manifold? Right? The answer is no, because I have nowhere used the slow manifold idea at all. Right? This is just some kind of quasi-steady curve, but it doesn't respect invariance at all. Right? I've never used the fact that there's nothing to tell me that once I'm on this kind of funny surface, I will stay there. It's also some surface. It's a surface that you get if you make this quasi-static assumption. So let us compare that thing, right? So if I set epsilon to 0, I get this quasi-steady state. Right? There are innumerable problems where you will find this assumption being used as a first approximation. Okay? but it's not the same as the slow manifold. For one, you can see that there is no reason it is invariant because I have not used that anywhere. And secondly, there is no way to iteratively correct this. Whereas a slow manifold, I have an exact equation for h of x, which I can then try to solve to some degree of approximation. Right? Here, there is no such thing. Anyway, for a simple example, we can compare it. Okay, and you see that it doesn't actually work very well. I mean, it works okay, but it's not exact. So the red line is the steady state, quasi steady state approximation, where you just put the derivatives of the fast variables to 0. So what will happen then is, where you have a set of ODEs, for all the fast ODEs, you put the time derivatives to 0, they'll become algebraic equations. So you will get a differential algebraic system. Right? If you solve that, that will be like some kind of approximation, uncontrolled approximation, which is not exactly the slow manifold. So sometimes it works reasonably well, like here is okay, not so bad. Sometimes it can be completely wrong. So this is what one would call an approximate, not an uncontrolled approximation. You have no idea what is the error, etc. So this is not advisable, but you'll see in many problems as a first thing this is done. And your question should be you should always go on to check it. Anyway, so now let's come back and do it properly. So we go back to our scaling in terms of the fast time because that shows it in this slow manifold form. And now I can try to get the slow manifold. So I'll skip some of this first and let's go quickly to this so that you see what is happening. So you see now I have this, this is exactly what I wrote, right? This is the equation on the manifold, which I can use to get an equation for H. And in general, this is a nonlinear thing, okay? Because H appears also in its derivative and so on. But, in this case, in fact, H is not nonlinear, but it can be. But I can solve it, I'll use this perturbation form. And when I do that, you can get an exact solution for H, only in this special case. Otherwise, it will be some approximation. But I get this solution nonetheless, x upon 1 plus x, which is very different from the expression you got, right, for the quasi-static thing. And when I substitute, you see, now it is, of course, much better. So it completely sits. The blue line is what's the slow manifold. It sits on top of, it is exact, right? It sits on top of what you are. In this case, it's exact because, like I said, it's a simple problem. There is no epsilon coming in this expression. That means it's always correct. Generally, you will get some approximation for H. So then as epsilon becomes bigger, it will not be as good. But here it always works correctly. And you can see if epsilon is 0.1, that quasi-steady state is not bad. But when epsilon becomes 0.3, the quasi-steady state starts deviating from the exact slow manifold. Okay, so that's nice, but now the question is, how do I apply this kind of idea to more general systems? Okay. Here there was a big simplification in that the system was already split into slow and fast directions. Right? So I had x which was slow and y which was fast. But this need not be the case. Even in this 2D problem, I could have had epsilon coming in a mixed way. Right? So that there was in fact a slow direction, but it was not aligned with either x or y. Because x or y would be some physical variables, right? But the slow direction of evolution of the system can be in some combination of them. Right? It doesn't have to be that x and y are separate. So then how do I generalize this? This is particularly important when I start looking at PDEs. Because, for example, if I think of a concentration field, the entire concentration field will, of course, not evolve slowly. Right? There may be a particular distribution of concentration to which the field approaches, and then that evolves slowly. So a very simple example, which we will see in a second, is the well-mixed kind of problems, right? So if, for example, you have some system in a tank which is being stirred, and you start with some arbitrary distribution of concentration. When you say stirring is fast, we assume, okay, very quickly it will become uniform. And then if there is some evolution, maybe some reaction is going on, you will say, okay, everything is uniform. Now I can study how the concentration varies because of some reaction. So in this slow-fast splitting, right, the reaction dynamics are slow, and the mixing that is happening is fast. And we make an engineering approximation right in the beginning and say, okay, I'm going to assume uniform concentration. But what allows us to do that is really the same thing. Right? What is happening is the concentration field, which has infinite degrees of freedom, right, Because of the fast mixing process, if you start with some arbitrary variations, they will quickly homogenize. That means you'll collapse onto the slow manifold. Here the slow manifold is just a uniform concentration, but it need not be. It could be some other concentration distribution. Okay, so I need to find, if you like, the direction in which things are slow, on which things will collapse. So the coordinates are not always going to be so simple. So in order to generalize that, okay, there is some formalism which will be important when we ultimately come back to our stochastic processes. So the point is, I can start with some equation. Okay. This f also involves the time derivative, so maybe I should use the board to help. So if I don't have this slow fast splitting right in the beginning, right, I just have some dynamical system. Okay, so let's say I start with some nonlinear dynamical system, right? I have x dot, some function of x and epsilon. And there are some slow dynamics, some fast dynamics. I know this because if I, let's say, evolve some trajectories, I see some rapid evolution and then things slow down. Okay. But there is no automatic splitting. It's not that if this is a vector from x1 to xn, that x1, x2 are slow and the rest are fast. Why should this be the case? There are some directions in phase space which are slow and some which are fast. Okay. So then how do I generalize it? Well, everything is usually happening around some kind of fixed point, because it's only in the vicinity of the fixed point that things start to slow down. So I can find some fixed point which I'm interested in, right? And then I can linearize the problem. So I'll always be able to linearize this, right? And for small epsilon, so usually epsilon is connected to that linearization. And I can rewrite this problem, okay, as some linear operator which depends on that epsilon. Sorry, x. So I can always take a general nonlinear dynamical system and rewrite it like this, because about some fixed point. Okay. That means some state where dx dt equal to 0. Okay, so I can always rewrite it in this way. So I can split the nonlinear thing into its linearization about small epsilon, about some point, okay, about some fixed point where epsilon is then some parameter. And then I have some nonlinear part. And now the important thing is when epsilon goes to 0, okay, I will get an equation which looks like this. Right? X. This is now linear. Okay, so this is a linear equation. And if I have this behavior of slow and fast in the limit where epsilon goes to 0, I have those slow variables, then this L0 will have 0 eigenvalues. Okay, because that means dynamically those directions things are not moving at all when epsilon is 0. In reality, epsilon will be something small, so things will move slowly. Okay, so in other words, this L epsilon will have some directions where the eigenvalues will be small. Those are the slow directions, some which are fast. Okay, and when I take that epsilon to 0, those slow eigenvalues will actually become 0. Okay, so this L0 has a null space. Okay. So those of you who don't know this should go to a quick linear algebra refresher. Okay, but L0 is like a matrix, especially in this problem. Generally, it's a linear operator. Okay. If it has a 0 eigenvalue, that means this dynamical problem can be diagonalized, right? Each mode of x will evolve independently along the eigenvalues of, along the eigenvectors of L. And if you have a 0 eigenvalue, then along that direction, nothing moves. This is the ultimate version of slow. Okay. So if L0 has no zero eigenvalues, they're all far away from zero, then everything is on the same speed. The only thing of interest is if L0 has a zero eigenvalue, which means L epsilon, when that epsilon is non-zero, that particular direction, things will evolve slowly. Okay. So typically L0, I'm interested when L0 has a null space, right? Or that's also, or a kernel, right? So the kernel of L0, right, it's not empty. And in the simple case, let's say it is one dimensional. So in this, of course, it can be multidimensional in that space, but in the simple case, let's say there's only one slow direction. Okay. Then the basis for that slow direction will be the null vector of this L0, will be the eigenvector corresponding to the zero eigenvalue. So that's what I said in that slide. Okay. And now what's interesting is that because of this, this gives me the basis to split the system. Because I know that as epsilon is small, right, then the slow dynamics are happening along the direction given by the eigenvector with zero eigenvalue. So that, if you like, is my slow direction. And all other directions where the eigenvalue is non-zero will be evolving fast. So I can now, that gives me the coordinate system. I can split my dynamics into the slow and fast direction by using this null space vector. So that means I can write my x, right? So I can project the vector x, right? I can split it into two parts. Its projection onto the slow direction, which I now know, right? The psi naught. This is simply the, remember, it's the zero eigenvalue, the eigenvector corresponding to the zero eigenvalue of this operator, linear operator. Okay, that's suffice when you take epsilon to zero. So that gives me the slow direction. Right? I just project x on the slow direction. So I can write x as its coefficient along the slow direction plus the remaining stuff. And this is all the fast guys. Okay, so if you like, I have in some way, I've not got a new coordinate system entirely, but I've identified one coordinate alpha, right, which gives me the projection of the dynamics on the slow direction, and then I have everything else. Okay, and of course, this alpha is just, if you have inner product defined in your space, you just project it onto the psi naught, right? This I should of course normalize properly so that the projection makes sense. Right, so I can do this thing. And then what is my slow manifold? So the slow manifold is just knowing these variables x tilde, right, which is some vector, right? Not in terms of psi naught, of course, because that's a fixed direction, right? But in terms of alpha. Right? So let's say I have a 5-dimensional system with one direction which is slow, right? Everything collapses onto one curve. Then the slow direction near the fixed point is psi naught, right? But I still have x tilde is still a 5-dimensional vector. But the point is each of its components will depend on alpha. So then I will get 5 dimensions reduced to a curve, right? By varying alpha along the curve, that's how I'll define the curve. Right? I can find the point in space, how it moves just by varying alpha. If x tilde is given as a function of alpha, of course that entire function should depend on epsilon. Right? Epsilon is a small parameter. The shape of the curve will change in general with epsilon. But this is the slow manifold. So this is the general way of writing what I had written before, that y is some function of x. Right? If you generalize, it will be all the fast variables, right, are some function of the coordinate along the slow direction. Right? In the slow direction is this null space vector. Okay. Now the question is, how do I find this x tilde? I need an equation. So remember, before I got it from the y equation. right? And the X equation gave me the reduced model. Here I have only one big system, right? But I can use that same projection because this vector exists, right? And I can use the projection. So I can project this equation onto psi, and I can look at the complement of that equation. Okay, so I can calculate this. So I have the reduced model. Right, so what I've written on top. Right, so if I apply the projection to both sides of this, right, I'll get d dt of this guy, and then I just have to project the f. Right, so I simply project out the original equation onto psi naught, right, and I'll get the evolution equation for this coefficient alpha. And if I know alpha evolves and if I know the slow manifold, then I will know x, of course. But to solve this equation, you can see it's not closed, right? Because x has to be this stuff plus x tilde. I need the equation for x tilde in terms of x. If I know it, then this is a closed equation. So the closure will come from the remainder, the stuff that I didn't throw out. Right, so the other equation, right, and so these two things are just the splitting of this original equation. Right? If I project it onto psi, and then I cancel psi naught from both sides, that is this, right? And the leftover stuff is just this, right? 1 minus that is just this. Okay, so this gives you an equation for x tilde, and this, of course, I will write using my slow manifold, right? Yes, so if you like, I'll have and d alpha dt I know from here. So again, I substitute. It's the same thing that I had done before. But this is, of course, so this x tilde hat is what we want to find, right? So that is, of course, part of the mapping. This is, if you think of this as h and alpha as x, you will get exactly what we did in the 1D case. Okay, so this kind of splitting is called the Lyapunov-Schmidt reduction. Okay, it's it's technique of linear algebra, which has around it the idea that I have, when epsilon goes to 0, I have a linear operator with a null space. Then I can construct a kind of perturbation thing based on this splitting. It's used in different contexts. Okay, so this is one place where it finds use. Okay. But if you don't want to worry about it, the basic idea is that once you find the slow direction as the null space of this operator, then I can split the entire system on the null space and off the null space. And then I can use the directions of the null space are the fast directions. And you can then specify in that coordinate system the slow manifold. And then you do the usual thing. Okay. Now, at the heart of this, why this Lyapunov-Schmidt thing is a deal and so on, is that you could always say, can't I always do this for some arbitrary vector? The answer is no, because I can split it like this, because I know that these vectors will span my space. Right? So if you go back to linear algebra, if you know that I have a finite dimensional system, then the null space and its complement span the entire space. Right? If you remember this. Otherwise, I cannot just take some random vector and do this business. Right? The whole idea is that because it's a null space, then I know the null space of this operator and its complement can span this space, and I can use that to represent the function. Okay, that's why this is allowed. That's one caveat. Second is when I define this projection, I have projected onto the same null space vector. This is true only if the operator L0 is self-adjoint. Okay, in general, I should do this, right? Where belongs to the kernel of the adjoint operator. Okay, so these are mathematical details. If you are new to it, don't worry about it. Right? You can. It's not essential to what's going to happen later. I mean, it's essential to implement it, of course, but not for the general idea. Okay. So the point is just that if I want to project x onto a certain vector, how do I do this? Right? If I'm in an orthonormal basis, then I can directly project it onto the vector itself. But in general, this need not be the case. Okay. So one way to make sure that I project myself onto the vector, in general, is to find the null space of the adjoint operator and project on that. Okay, so it's like a bi-orthogonal basis. But if this L0 is symmetric, then it's the same vector. In other words, if you go back again to matrix algebra language, it's like saying the null space, right, of a matrix A. To calculate it, you find the null space of the transpose of that matrix, or the null space in the column space is orthogonal to the null space of the rows. Okay. Anyway, so that's important because it gives us the way to split the coordinates into slow and fast. Okay. Now, just as a final point, in what we'll do in the later classes, we will use this splitting, just because it is also consistent with what Gardner does in his book, ultimately to derive the Stratonovich limit. Okay? But one need not necessarily do the splitting, because the calculation itself can point you to the appropriate projection. Okay, so just to make that point, if you look at this equation, right, for x tilde, and I replace this f, right, what I'll get is so remember f is that L epsilon, right, x. Minus blah, 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 okay. So that is the equation to try to find the slow manifold. And if I construct an approximation, right, an approximate solution about epsilon going to 0, right? Then you will see that to calculate this, x tilde, okay, so yes, so now the important thing here is the L, right, so L epsilon will act on x, okay. Yeah, let us leave it like that. Now when I try to construct the solution about epsilon going to 0, I'll get L0 acting on x tilde, right, because L epsilon will go to L0 when epsilon is 0. X in general is split into the x tilde plus the null space, but the null space part will go to 0. Right? So I'll get all of this is equal to some right-hand side. Okay, so let me just repeat what I was saying. So my point is that even if you don't do this splitting, you will realize that one will have to worry about the, projection. Because if I start with this equation and I simply say that, okay, I know that there is a slow manifold, let me substitute that here. Then x dot will be replaced by dx by d alpha dt. Okay, that's what I have here. And then if I look at it in this way, I'll get L epsilon acting on the vector x plus epsilon and all linear stuff. Now I want to calculate x as a function of alpha, that is the slow manifold. And I have not bothered about doing the splitting. I'm just saying on the slow manifold, all the variables will depend only on one thing because I have a one-dimensional slow manifold. Right? So then I try to solve this equation for small epsilon. The leading order behavior will always be this term with L naught. When I put epsilon equal to 0, I'll just get L naught x equal to 0. That's the first equation. That will immediately give me the null space. Right? So first I will get okay, so when I try to construct the perturbation solution, when I put epsilon to 0, right away I'll see L naught x equal to 0. So the leading approximation to x is just lies on the null space with some arbitrary coefficient. So that's how I will get this first term. Okay. Then if I go to the next order, again I will have this operator L naught acting on the vector x, right? And then the RHS stuff, including this time derivative. No. Yeah.
Why does the projection of f along the slow direction disappear?
I'll come back to that later. Let me finish this. Okay, so I will have this system and I'll have to solve it perturbatively. In which case, to get the next correction to x, I'll have to invert the L naught. And if you remember, inverting L naught is like solving the system. Right? I cannot invert L naught in general when it has a null space. Okay, because some part of x will go to 0. It will never match this right-hand side. The only way I can get a solution is if this right-hand side lies in the range of the operator. And to do that, to make sure this lies in the range, I have to project out the stuff that's not in the range. And that thing is precisely the stuff that lies along the null space. So that is the complement in finite dimensional systems, which extends to certain PDEs also. Okay? So to make this thing solvable, it's called the solvability criteria, I'll have to project this entire equation out along the null space direction and make it 0. Only then I can solve this equation at all. Only then L naught inverse is defined. Okay, this is like the problem when you have more equations than unknowns, right? You are not guaranteed a solution, right? Unless the right-hand side is special, right? It should lie in your range of the operator. Otherwise, you cannot do this. Right? So that will happen whenever the matrix has a null space, and then you do Ax equal to B. B must lie in the range of the operator. Otherwise, you will not get a solution. Right? So that's the equivalent of doing it here. To guarantee a solution, I will be forced to project this equation along the null space. When I do that, I will get immediately this reduced problem. Because this is the projection along the null space. Right? And at each iteration, I will improve that equation. And then to make it in the range, I'll have to subtract that out, to put it to 0. That will give me this equation to correct. And then I can invert this. Okay.
Just f(x)t minus the projection of f along the slow direction. Is that being referred to as RHS?
No, RHS is different there. It's all what I collect from this thing. Just a shorthand.
RHS is L epsilon x versus epsilon and x.
Yeah, the leftover stuff after I do this. So if there will be some L epsilon which is not in L naught, etc. If you set up the perturbation problem, the point is when you set up the perturbation, you'll get some right-hand side. You'll get this time derivative term, okay? And you will have this linear operator which has to be inverted. So to invert it, I'll have to project this equation on the null space, put it to 0. That is basically going to give me the equation for d alpha dt. And when I look at what is left over, there I can invert. But that stuff will be similar to this because this is the complement. This is what lies in the range. So to summarize, if I were to naively solve this for the center manifold, I would inevitably encounter this splitting because I'll have to project out the perturbation equation onto the range, onto the null space, and so that I can make the complement of the range 0, so that what's left over, the RHS lies in the range. Then I can get a better approximation to the slow manifold. So in trying to approximate the slow manifold, I will automatically get the equation for the evolution on the slow manifold, this alpha dot. So that's one way to do it. The other way is, you know this a priori that I'm going to do this, right? So I directly split the problem into slow and fast. Then it's guaranteed to lie in the range, right? That's why here I didn't bring it up. So when you do the splitting beforehand, you directly already get the equation on the slow manifold. You get the equation for the slow manifold itself. And that is set up in such a way that the RHS lies in the range. Because you see, I have my general RHS, and I've subtracted out the part that is along the null space. This minus is exactly what is needed to put this right-hand side in the null space of the operator L, which will lie here. Here I have not shown it because the L's and all are buried. Okay, but it's the same idea. So in other words, the Lyapunov-Schmidt reduction is a way of guaranteeing that the solvability is satisfied. Even if you don't do it, you'll be forced to do the same thing. So it's not that if you don't do Lyapunov-Schmidt, you cannot get the center manifold. Okay, so let's go back to our specific example on the slide. And here, once again, the emphasis was that it was already split for us. That is, in fact, the major simplification. X is slow, Y is fast. Okay, how does this work out now? I should be able to see it in terms of my Lyapunov-Schmidt splitting, right? So if I use these ideas on that example, on this example, I'll see about the fixed point 0, 0. I have the following general linearization, L epsilon. Okay, so this is the matrix. This is the linearized matrix of that nonlinear system. And when epsilon is equal to 0, where I expect there to be a separation of time scales, L naught becomes this simpler system, which clearly has a null space corresponding to 1, 0. So in other words, the eigenvalue in the x direction is 0, correct? In the y direction, it's not 0. Fine. So what we saw a priori, now we see properly from the operator theoretic thing, right? That I actually get a null space vector which is 1, 0, which means the x direction was a null space. That's why the x coordinate was like my alpha. It happened automatically. Okay. So if I now project the equations onto psi, I'll get only the equation in the x direction. So this is the slow equation. The complement of that was the y direction. So that was the fast equation. And now the slow manifold is fast variables being expressed as function of the slow, which is y as a function of x. Okay. And then we do exactly what we had done. But even if if I take the same system and rotate it, I change my coordinates. Instead of using x and y, I use some x tilde, y tilde, which is some rotated coordinate system. Then the split will not be obvious, right? Because then what is 1, 0 here will be some other direction if I just rotate the coordinate system. But that should not stop me from finding the reduced model. Okay. So the general Lyapunov-Schmidt splitting I showed you will always work. And importantly, it will extend to PDEs also for certain class of PDEs. Okay. For certain class of PDEs, you can show it rigorously. But for others, you can anyway do the calculation in an applied math approximation style and very often get useful results. Okay, so I know I've covered a lot of ground because this is not a course on reduced order modeling. Okay, but I wanted to put all this stuff down so that you can go back later and when you have more time, you want to revisit this question of order reduction and then how it ultimately relates to stochastic modeling. You can come back and look at this lecture and maybe each thing I said about the null space and so on, you can understand that more carefully. Okay, but so in that same spirit, let me just show you an example of these applications to a PDE, so you see its relevance. And then in the next class, I'll actually work out a PDE problem, which is something you all know familiarly already. Okay, so you will see how this thing works there. And then we'll finally come back to our stochastic problems. Okay, so let's now consider these ideas in a PDE. Okay, but now because we have thought about things in a generalized operator theoretic way, it will be very easy. So let's say I have a PDE for a concentration field. Okay, so let's focus on the slides now. And the PDE is just a concentration reaction diffusion equation. Okay, I have dc dt is equal to linear operator acting on C and some nonlinear stuff. okay, which is small. So epsilon is a small parameter. And it's a reaction diffusion problem. So the linear operator is just dou square C by dou x square. Okay, when I say linear operator, it just means that, I mean, it's satisfies superposition, right? You can think of it as a matrix, right? So if that's easier, if I were to discretize this, so LC is just diffusion, d square C dx square, minus, think of n as some nonlinear reaction or convection or some other term, right, which has epsilon in front of it. So the epsilon will come from scaling the system properly. It just tells you that whatever is there in n, reaction, convection, etc., it's slow compared to diffusion, which is very often the case. If I take a catalyst slab which is very thin, right, or I think of heat transfer in a thin fin and so on, the diffusion process will be fast if the dimension is small. And any other process, whether it is surface convection or surface reaction, bulk reaction, those things will be slow. Okay. So returning to the equation now, you have this structure that dc dt is equal to LC minus some nonlinear stuff, other stuff which is small. Okay, and what I want to do is reduce this system. Why do I think so? Because I think the diffusion is fast, right? So it will somehow simplify the concentration field, and I want a simplified equation for the slow evolution after the rapid diffusion is over. So in a heuristic way, if you like, if the problem is very simple, then diffusion will just homogenize everything, and any variation because of reaction and so on will happen to the homogenized concentration. So I can replace the PD with just one equation for the average concentration. We'll see that in a second, but there can be more non-trivial versions of this. But the intuitive idea is diffusion is going to happen quickly. So all rapid concentration fluctuation should be quickly evened out. And somehow I will have a smooth concentration profile that will evolve slowly. But the question is, what is that profile? How do I find it? How do I get the simplified model? In a kind of non-rigorous engineering way, one might say, okay, let me just replace C by its average because diffusion is fast. But we'll see that doesn't always work. Okay, so suppose I want to apply the ideas I had today. Right? You'll see that this matches my general prescription, except this is now a PD. Earlier we were in finite dimensions, but I can always, either I can proceed, if you know operator theory and functional analysis, this will not create any problems. Even if you don't, to make progress, you can think of discretizing this PD with n grid points. Then it will become an n-dimensional problem. And then you can do everything I just said. Okay. Fine. So now let us see what are the requirements, right? What I need is as epsilon goes to 0, I will get an equation dc dt is equal to LC. And in that limit, L must be singular. That means it must have a null space. If it does, then I can do my slow manifold business, right? So let's assume it has a null space. I'll call that psi naught. Right? So now psi naught, because it's a PD, will be some function. Right? A function is like a vector in infinite dimensional space. So again, if I discretize, this psi naught will be discretized on some n grid points, so it will be an n-dimensional vector. If you go now back to function space, it's just a function. So this is nothing but actually the shape of the concentration field that is produced because of rapid diffusion. Okay, that's its significance. So this will be some vector with 0 eigenvalue in the limit of epsilon being 0. That means diffusion is truly infinitely fast. And then I can say there must be some slow manifold which will be some constant coordinate times the psi naught. Okay. So let's see this in action for the case where I have a no flux boundary condition. So I take this PD, dc dt is equal to d square c dx square and some nonlinear reaction on a 1D domain with no flux boundaries. Okay. Remember, if you are doing differential operators, they are not defined unless you put the boundary condition. Right? So now with these boundaries, if I look at what is L, what is the linear operator L? It is this thing, d square c dx square, right, with no flux boundaries. So if I put d square c dx square equal to 0, that is like looking for the null space. If I have dc dx equal to 0, there is a null space, right? Any constant will become 0. d square dx square of any constant is equal to 0, and it will satisfy the boundary conditions. If I Dirichlet conditions, it will not happen, right? It's only because I have Neumann. So fine, I do have a null space. In this case, the null space is just, I mean, of course, up to a constant is just 1. That means the concentration profile is uniform on that null space. Okay, so now it's easy. I can define my coordinate system by projecting it onto the null space. So the projection of the concentration field onto the null space, remember in, again, infinite dimensions, the inner product is an integral. So it's integrating the concentration field on the null space, which is 1. Again, this d square c dx square is self-adjoint, so then this is fine. Importantly, the inner product is just the average concentration. Okay, so interestingly now, when I try to find the coordinate, I project C onto the null space, I get the average, cross-section average, which is actually the physical variable we usually define. So heuristically, we would say, look at the average concentration. That is actually the projection on the slow manifold. That is the coordinate on the slow manifold. Okay, so I can write my general concentration field as projection on the null space, which is the cross-section average, plus deviations from the average. Right? And this is, the integral of this must be 0. That's what's written here. That's the definition of the C tilde. Okay, so then this is my equation now. If I project onto the null space, that's like just integrating this guy. Okay. And so then I will get the equation for the cross-section average, right? The integral will come into the time derivative. This d square c dx square will go to 0, because if I integrate and put the boundary conditions, it goes to 0. That should happen, in fact, because I'm projecting it on its own null space. And so what will be left is just this nonlinear term, but averaged out somehow. So I have this is the averaged equation. The problem is I need to know C tilde, the deviations from the average. Otherwise, I cannot close this, right? Because R depends on the whole C, not just on C bar. So I go to the same equation on the off the null space, right? That looks like this. Again, I have to invert this d square dx square. To invert it, the right-hand side has to be in the range space. Because I've already projected out, it will take care of it. Finally, you will see that in this simple problem, C tilde equal to 0 is an exact solution. That means not that if I solve this problem numerically, there will be no deviations from average. Of course not. It means when I collapse onto the slow manifold, the entire concentration field is just uniform. That means C equal to its average is the approximation on the slow manifold for this simple problem. So the reduced model becomes very simple. It's equivalent to replacing C by its average. Precisely because the slow manifold shape is just uniform now. There are no deviations. Okay, this is only with no flux boundaries. So what you would naively do if you looked at this equation, right, and say, oh, I have very fast mixing. This phi by it is the Thiele modulus. Right? If this phi is very small in reaction engineering, right, we'll say, oh, okay, diffusion is very fast. So to get the equation on for the reaction, I will just replace C by its average. Right? That's the equation we have here. This is a slow manifold approximation accurately only with no flux boundaries. Okay. So this is the simulation of this for this particular reaction. I'm taking different initial conditions. You will see that right, slowly it will, yeah, this is what you're seeing here. This is the general initial thing. It slowly collapses onto a flat line. This is in time. Okay, and then it evolves being completely homogeneous. That means the diffusion rapidly homogenizes everything, and then it slowly evolves. And if I look at the average concentration, it's exactly predicted by my reduced model. I compared the PDE with the reduced model. Okay. This is at a larger Thiele modulus. It takes longer to relax. But interestingly, the cross-section average is always well predicted. This is because my reduced model was exact here for Neumann conditions. Okay, now let me close by saying I have the same problem, but again in the catalyst lab. This time, instead of dc dx being 0 at the walls, I have C as some fixed concentration, C naught. Okay. Now you see that I cannot have a concentration field inside that is completely flat, even at infinite time. I mean, even when I'm on the slow manifold. Why? Because at the ends it has to be fixed at C naught. And if the concentration has to evolve, it cannot be flat. If it is flat, it is always C naught, it cannot evolve because the boundaries are fixed at C naught. So it has to be something evolving inside the bulk, but whose ends always come to C naught. So it cannot be a flat line. So now you can see that the long-term shape of the concentration, which is basically the slow manifold, cannot be flat. It could be flat only when I had no flux boundaries, not when I put Dirichlet. So now my machinery will be useful. Right? I'll do the same stuff again when phi, which is like epsilon, is made 0. I'll see that I have dc dt is equal to a linear operator, the diffusion operator. In this time, However, it's not singular, right? Because it does not have a null space. This I will skip a little quickly, okay? Because so what is done here is I can fool the problem, right? Instead of having dc dx, instead of having c equal to a constant, I can say dc dx is some flux adjusted such that c is always c naught. Okay? And I can then multiply that flux by some parameter alpha and take alpha going to 0 and then later put it equal to 1. So I can do an approximation for small alpha and then later set alpha equal to 1 and hope it works. I'll skip some of these details, okay, but yeah. So this is the numerical calculation, is the blue line. Okay. After doing my slow manifold calculation with some tricks, I get the dotted line. Okay. And you can see how it collapses. So initially I purposely start with some funny concentration profile, which is very far from the slow manifold. But very quickly, look at that time, right, which is non-dimensionalized with the diffusion time. By the time the time is at about 0.1 of the diffusion time scale, I've collapsed onto this thing which is like a parabola. Okay, so whatever weird concentration you have in the catalyst lab, diffusion will quickly homogenize it, but now homogenization doesn't mean uniform. It means it collapses onto the slow manifold, which is a parabola. It's parabola because the boundary conditions are forcing it to remain a parabola. Okay, so here you see an example where there is a fast process. Diffusion is the usual fast process, right, in many problems. It homogenizes it, but that doesn't mean that it becomes flat, right? It means it approaches the slow manifold, which is not flat because of my funny boundary conditions. Now, this should immediately cause you some interest in a stochastic thing because diffusion is the outcome of Brownian motion. So if I go back to a stochastic process where I have Brownian motion, right, in terms of the continuum description, Fokker-Planck description, that will appear like diffusion. So when I say diffusion is fast, it's like saying I have a SDE with rapidly fluctuating noise. And the actual aim of the noise will be to mix things, to diffuse things. So you can see if I were to write this is the continuum version, reaction diffusion equation, I could have written the stochastic version of it, where I have the Wiener process and I have some drift term which accounts for the reaction. And if the reaction is weak, I should be able to do some kind of reduction just like this. So this is the connection we will exploit later on to get the white noise limit. Okay, so let's stop here. To summarize this rather heavy lecture, okay, the point was that in many dynamical systems, you have fast and slow directions, and it is then possible to collapse the system to do model reduction and get a model only for the slow directions. And the key thing there is to find the slow manifold, which is the curve that describes how the fast variables evolve as a function of the slow variables once you wait for long enough time, once all the transients die out. So I'll apply this again to another continuum concentration mixing type problem in the next class, specifically TLRS dispersion, and just so that we understand the technique. And after doing that, we'll come back to our stochastic problem. Okay, thank you.